In the following set of videos, we'll try to understand how to sketch graph of a rational function. Now there are some critical parameters which we should consider before sketching a graph of a rational function. Function given to us is f of x equals to 2x squared plus 17x plus 21 divided by x squared plus 6x minus 7. Now when you see this kind of a function, you can find out a couple of things. One, of course, is that we have a horizontal asymptote at 2, since the degrees of numerator and denominator are same, right? So ratios of leading coefficients will give us horizontal asymptote, which is 2 here. Now we have quadratic functions in numerator and denominator, and they can be factored. Once we factor these, we can figure out about all other things, for example discontinuities mainly, right, which will give us domain and range also. As far as intercepts are concerned, well, if we plug in x equals to 0, we get the y-intercept, and if we equate for f of x equals to 0, that is y equals to 0, we get the x-intercept. So those things we'll find after factoring, right? So these are the things which we are going to do to analyze this function, and then we will sketch our graph. Okay, so first thing is, let's try to factor both numerator and denominator. Okay, so in the numerator we have 2x squared. Well, let me do it on this side. So in the numerator we have 2x squared plus 17x plus 21. So what we are looking for are two numbers whose product should be 2 times 21. So we are looking for two numbers whose product should be 42 plus, right? So P and Q, let me write Q and P now, and whose sum, that is Q plus P, should be equals to 17, right? So the two numbers could be, so like you can try numbers, 6 times 7 gives you 42, but 6 plus 7 is 13, not 17. So that really doesn't match with us, right? So we can try the next number. Instead of 6, let's try 3. So 3 times, so let's divide 42 by 3. So 3, when you divide into 42, 3 times 1 is 3, and then 12 is 14, right? So we get two numbers, and our numbers are 3 and 14, right? When you add them, you get 17, and when you multiply them, you do get 42, correct? So that gives you an idea how this can be factored, right? So we can now factor the numerator. Now similarly, we can also factor denominator, right? To factor denominator, we need product PQ as minus 7, right? That is what we need. And when we add it, we should get P plus Q as equal to 6. So the two numbers which should get this result is one should be negative, one should be positive, right? So the two numbers are 7 and 1. 7 times 1 is 7, and one of them has to be negative. The smaller number is negative, since we need addition as positive, 6, correct? So that is how we try to factor our quadratic function, right? So now I'm not getting into details of factoring more than this, but what we can do now here is we can write f of x in the factored form using these factors, correct? So we have done our analysis, and we can say, well, f of x, so okay, let me give you. So 2x squared plus 17x plus 21, let me start here now. We will use this knowledge, right? So we have 2x squared plus 17x plus 21. So this, we found that the two numbers are 3 and 14, right? So let's write 3 and 14 instead of 17. So let me write here 2x squared plus, let me write 14 here, 14x plus 3x plus 21. So we are dealing into numerator, right? Now from these two, we can take 2x common, and we get x plus 7 here, and from here is 21. So we can take 3 common, and we get x plus 7 on this side also. Now x plus 7 is a common factor in both these terms. So we get 2x plus 3. So that is our numerator. Okay, always when you see a rational function, it is px over qx, right? Where p and q are polynomials and qx cannot be 0, correct? So this is our numerator, that is px, correct? So we get px in the factored form. Similarly, we can write qx. Now qx in the factored form is, we found the two numbers to be 7 and -1. So that could be written as x plus 7 times x minus 1. So we got it factored form. So we can write our function f of x now as equal to x plus 7 times 2x plus 3 over x plus 7 times x minus 1. Now, this leads to a rational function in factored form. So this is a very good form to analyze. So from here we can say a couple of things. That first thing, it has got two discontinuities, right? One of them is at 1, the other one is at -7. Another thing what you note here is that we have a common factor in numerator and denominator, x plus 7. Now this common factor, x plus 7, leads to the whole, right? So all the discontinuities because of the denominator don't really give you vertical asymptotes. It's a point to be noted, right? But if they have a common factor in both numerator and denominator, that leads to a whole, correct? So we found from here that we have a whole. So let me write down the characteristics which we discovered. So we have a whole, and the whole is at x equals to -7. That is first thing we found, right? Second, amongst the discontinuities, we also found that there's a vertical asymptote. Now, this does not have a common factor, right? So this is the only factor in the denominator. So we have a vertical asymptote, and this vertical asymptote is at x equals to 1. So we got our discontinuities, right? Now, let's look into the asymptotes. Now, asymptotes are very, very critical and important parameters to define our rational function. So, while the degrees of both numerator and denominator are same, right? We already have vertical asymptote with us. Now the other asymptote could be horizontal asymptote. So let's figure out the equation of horizontal asymptote. Since the degree of both p and q are same, we have a horizontal asymptote, and the equation of the horizontal asymptote is the ratio of leading coefficients. So it is y equals to 2, right? I hope you remember how to figure out this. Well, horizontal asymptotes are always defined when x approaches infinity, plus or minus, or when x approaches minus infinity, right? So these are the two places where if a function approaches a fixed value, then we say that fixed value which function is trying to approach is the horizontal asymptote. Do you understand? So in this case, if x is very large, think like this. If x is very large, then 21 is negligible, 7 is, these numbers are negligible. X square is very, very large, and therefore these terms are also negligible. We are left with just these terms. Do you see that? What we are left with, if x is very large, in these conditions, we are actually left with these terms. Do you see that? So ratio x square gets cancelled, and we are left with 2. Do you understand? And that is why we get horizontal asymptote y equals to 2. I think it's kind of important reminder for all my students that that is the reason why we are always taking leading coefficients ratio as horizontal asymptote when the degree of numerator and denominator is same, right? We'll consider other cases in different videos. Sure. Now, we got the horizontal asymptotes, and now important points to consider for us are the intercepts, right? So x-intercept. So when we are dealing with x-intercept, that means we want to find the value of x where the graph will cross x-axis. And at that point, f of x will be 0, or y value is 0, right? Now, we say f of x is 0. When can f of x be 0? So let me first write this in a form that says, we'll write this as 2x plus 3 over x minus 1. An important thing here is, whenever we write like this, we have to write restrictions that x is not equal to minus 7, that is taking care of this whole, and is not equal to 1, which is this vertical asymptote, correct? So that is most important to write. Now, let's get back to the intercepts, right? So first, let me do Y-intercept. So we say Y-intercept. Now Y-intercept is a point where x is 0, correct? So wherever the graph crosses the y-axis is your y-intercept. If I put x equals to 0 in this equation, what do I get? I get 3 over minus 1, which is minus 3, right? So y-intercept is a point where x is 0 and y value we just found as minus 3. So that is our y-intercept. Now, as I said earlier, we'll come back to x-intercept, right? X-intercept. X-intercept is a point where y is 0. And we are trying to figure out where will the graph cross the x-axis. That x point is the x-intercept. Now, if y is 0, that means f of x is 0. That means numerator should be 0, right? And numerator can be 0 for the value of x equals to minus 3 over 2. So minus 3 over 2 or minus 1.5 is your x-intercept. So you see, we have got all critical parameters which will help us to sketch a beautiful graph here. Correct? So let's try to sketch a graph now. So it's time to sketch a graph. So I know I'm running out of space always, but I'll use whatever we have. Okay, so let me draw here the axis, right? Okay. Now, first thing we should do is look for vertical asymptotes. Whenever you draw your graph, look for vertical asymptotes. So vertical asymptote is at x equals to 1. So that is my vertical asymptote. Let me just sketch it thinking. My rough sketches are good enough actually, but you should do these sketches on a proper graph paper so that you get neat and clean graph, okay? So that is my vertical asymptote, and let me label this here as x equals to 1, okay? Now, then the second thing which I should sketch always is the horizontal asymptote. So horizontal asymptote is y equals to 2. So let's say this is my y equals to 2, okay? So that is my y equals to 2 horizontal asymptote, right? So this point is 2 for me, this point is 1 for me, correct? Now what? Then good points to do is x and y intercepts. Okay, so what is the x-intercept? Minus 1.5. So if this is one kind of, so minus 1.5. So let's say this is 1, this is 1, minus 1.5. Let me write this as a point here, then I'll draw a graph going through this, right? But at least I know that this part is on the lower half, it's kind of like this, right? Now the second point of interest is the y-intercept. Y-intercept is minus 3. So minus 3 will be, let's say this is 1, this is 2, so this is, let's say, minus 3 for me, okay? So that is my minus 3. So I'm writing 1 here and 2 here, and that's my x-intercept, right? Now, these are good points to get, and as we see from here, now what we need to do for writing a very good, for sketching a very good graph, we should see the behavior of the curve near the asymptotes. That's kind of very, very critical. Now when I say behavior near the asymptotes, it means what? So let me discuss this now here for you. So what I'm trying to discuss here now is behavior near asymptotes, okay? So what we will do is, we know that there are two asymptotes. The vertical one is x equals to 1. Let's see what happens if x approaches 1 from negative side. Negative side really means that from this side. Do you see that when x is approaching 1, negative of 1, that means from the left side of 1, right? Left side of 1. That means what you should do is you can take a value here like 0.9. That's close enough, right? So if I took 0.9 here, then 0.9 minus 1 will be a negative thing, and numerator is positive. And we know it's approaching infinity, and since we get negative thing, so that means it is approaching negative infinity. Do you see? So you get this curve. So we can write here that as x approaches 1 from negative side, y approaches negative infinity. Correct. Now the second parameter is what happens if x approaches 1 from positive. That means right side. So this, I mean right, okay? And that was left side, okay? So that means now we are trying to approach from this side. So let me take a value 1.1. So if I take a value 1.1, this becomes positive, and that is positive, right? Positive, positive. 1.1 minus 1 will be 0.1 positive. So that means we are approaching infinity, but positive infinity. So that is my behavior near the asymptote, and I can write here as y approaches positive infinity. You understand? So that is the behavior of our graph near the vertical asymptote for the given rational function. Correct? We will do the same thing now for horizontal asymptote. So this behavior we did for vertical asymptote, right? Now let's do for horizontal asymptote. Now in case of horizontal asymptote, we are trying to approach infinity, correct? So as x approaches negative infinity, what happens? Negative infinity is if you plug in like -1000 in your calculator and calculate. So -1000 here will give you a negative value in the denominator, and -1000 there will also give you a negative value. So it's always positive, but the critical thing here is we are trying to approach 2. So do we get a value more than 2 or less than 2? That is the thing which we are trying to figure out, right? So that is what we are. So now let's look into it again, right? So in your calculators, just plug in the value -1000 and this, right? So we'll do this. So we'll say, so 2 times -1000 is -2000. So we'll say 1 minus 2000 equals to, and we'll divide by -1001, right? So we'll divide by -1001. So 1001, and we get something which is less than 2, right? So this is less than 2 is 199 over something, right? But it is less than 2. So that is critical. So we found that as we approach this, then y approaches 2, but this is to negative side, less than 2. That is kind of critical. So we are approaching here like this. Do you see that? That is important. Now, what happens when x approaches positive infinity, right? Then what happens to y? Does it approach more than 2? I mean, from above or from below, right? That is critical. So plug in 1000 here, right? So when you plug in 1000 here, if the numerator is more than the denominator, right? It's 2003. And here it is less than 1000. So obviously it is more than 2, right? So you're approaching 2, but from the above 2. That positive means positive of 2, right? That's what I'm trying to say. So that gives you fairly good idea of the graph now. Do you see? So if you see from left to right, always when you are drawing graphs, you have to see them from left to right, okay? Then you see this graph is approaching 2 from below, and then it has an x-intercept here at 1.5. Let me write here minus 1.5 here, and then this point is -3. So let me write down -3 here, and then it goes to minus infinity. So that is our graph of the left hand side, correct? So let me draw this graph now. So we get a graph like this, going down like this, and then we can connect these points with a smooth curve. And there you are. So that is the left side of the vertical asymptote, and we find all the way it decreases, correct? And now this graph, we can join this like this and then draw like this. So that's our graph on the right of the vertical asymptote, correct? Now, once you have sketched a neat and clean graph, now you have to figure out where the hole is. Don't forget about that, okay? So now let's look into the hole. Now we say x cannot be -7. Well, where should that hole be? So you just plug in -7 here, right? And do your calculation. So we are trying to figure out where the hole is, right? So we're trying to figure out hole. Let me write here now. So what we do is this equation, we write -7. So -7, okay. So let's write -7. This is 2 times -7 plus 3 over -7 minus 1. So we get -14 plus 3 over -8, correct? And you can calculate this value. -14 plus 3 is -11 over -8. So it is plus, but let's calculate what the value is approximately, right? 11 divided by 8 gives me 1.375. So the hole should have been at -7, 1.375. So that's the location of the hole. So -7 goes beyond my scale, but let's assume that this point is -7 for us, right? So here we have a hole, right? And we'll say, well, this is the position of the hole, right? We'll just call it H. And my point H is this, okay? So that's the hole, and the location of the hole is x minus 7, and the y value is 1.375. Correct? That means the graph is all the way, and we have a discontinuity, the hole here, right? And then the graph goes continuously. Correct? So this is the complete graph for us, and there is no harm. In fact, it is always good to label your axes, right? F of x, and this is minus x and this is minus y, and that's the origin for you. Correct. Now since you have a hole here, okay, let me not just highlight that the hole is not a part of our function. Do you see that? Hole is outside the function, so I'm just making this darker for you. So we exclude that part, right? So that is the final rational function for us, and that is a neat and clean sketch. Do it on a graph paper so that you get a wonderful sketch, right? Don't forget to label all your points. So this is minus 3 for me, and that is minus 1.5, and that is y equals to 2, x equals to 1, and the hole is I don't want to mess this up, but you understand, minus 7, 1.375. So that is the location of the hole. Now from this graph, I would like you to answer a few. You should write down, when is f of x greater than 0, right? When is f of x less than 0? When is f of x increasing? When I say when is f of x increasing, intervals during which it is increasing or decreasing, okay? So these are critical things which you can get from the graph now and answer those questions, right? You will find the graph is always decreasing. Do you see that? But when you write the intervals of increasing and decreasing, you should mention it's not increasing at all and it is decreasing. You have to break your interval at these two discontinuities. Do you understand? That is kind of important. So it decreases from minus infinity to minus 7, and then from minus 7 to 1, all those points not included, correct? Because they are not in your domain. And then it decreases from 1 to infinity. That is how you're going to write. Now when is it positive? It is positive, you have to again exclude this point, right? So it is positive when x is less than minus 1.5, not equal to minus 7. And it's positive when x is greater than 1. And it is negative when x is less than minus 1.5, correct? So these are your decreasing and increasing parameters. And one question which I haven't answered so far is the domain and range. So let me come back to domain and range now, right? So domain is x belongs to real numbers where x is not equal to these two discontinuities, minus 7 and 1. So right, will minus 7 and 1, correct? And how about the range? Range is very critical. Y belongs to real numbers where you can see that y is everything but just 2 points, right? Where y is not equal to 2, right? That's one thing. And second thing, that y is not equal to value of the whole, right? That is what is very critical. Y is not equal, that's why we found that answer, not equals to 1.375. So that point is not in our range. Do you understand? So if you miss these things, the whole position, then you miss a lot, right? Do you remember that? So have a good look at this graph and try to understand how we can sketch a beautiful rational function, correct? And then set of these videos on sketching rational functions, I'm going to take examples which will expose you to so many variety of rational functions. You'll be amazed. Thank you. Enjoy the journey.